Logarithmic functions. Here we define the logarithmic function. Let a be a positive number with a not equal to 1. The logarithmic function with base a, denoted by log with a subscript a here, is defined by log base a of x is equal to y if and only if a to the y power is equal to x. So log base a of x is the exponent to which the base a must be raised to give x. Now you can see that right here in the definition. So when we say log base a of x is equal to y and a to the y equals x, if these are equivalent, then y is the power of a that gives us x. So the way to read a logarithm is the power of a to get x is equal to y. So what's happening in a logarithmic equation and an exponential equation is that they are essentially the same equation from two different perspectives. So an equation in logarithmic form would be written like this. So the base is here and the exponent is here. And in exponential form, it would be written like this, where the base is in its typical spot for an exponential function, and the exponent would actually look like an exponent. So one of the main challenges with logarithms, especially when you first learn them, is just getting used to them. So let's take a look at the following example. Here in example 1, we have logarithmic and exponential forms of equivalent equations. And so we just want to understand why these are the same. So in logarithmic form, it is true that log base 10 of 100,000 is equal to 5. And this is because the power of 10 to get 100,000 is equal to 5. In other words, 10 to the 5th power is 100,000. And we know this because 10 to the 5th power means 10 times 10 times 10 times 10 times 10, right? 5 times. Likewise, log base 2 of 8 is equal to 3 because 2 to the 3rd power is equal to 8. Similarly, log base 2 of 1/8 equals negative 3 because 2 to the negative 3 is equal to 1/8. And finally, a little more abstract, log base 5 of s is equal to r must mean that 5 to the r is equal to s. So the main thing here is you just want to get used to the fact that these are equivalent to each other. We can use the definition of a logarithm to evaluate logarithms as long as the numbers are nice enough. So for example, we know that log base 10 of 1,000 is equal to 3 because we know 10 to the 3rd power is 1,000. We know that log base 2 of 32 must be 5 because 2 to the 5th power is 32. Likewise, log base 10 of 0.1 must be negative 1 because 10 to the negative 1 power is equal to 1/10 or 0.1. And finally, log base 16 of 4 must be 1/2 because 16 to the 1/2 power must be equal to 4. So as long as the numbers play nice here, you can do this without a calculator. But just think about the following. What if I had said log base 3 of 8 and I ask you, what does this equal? Well, the way to interpret this is 3 to that power must be equal to 8. And for this, we would not know how to do it without the aid of a calculator. So there's more to come on this. We have some basic properties of logarithms. We know that log base a of 1 is always equal to 0, and this is because a to the 0 power is always equal to 1. We know log base a of a is 1 because a to the power 1 is a. And here, log base a of a to the x must be x, and a to the log base a of x must also be x. And this is because logarithms and exponents are inverse functions of each other. So that's the other very important thing to understand here. And we'll talk more about that in just a minute. So for example, Suppose we have log base 5 of 1. We know this must be 0 because the first property says log of any base of 1 is always equal to 0. Log base 5 of 5 to the 8 power must be 8 because of property 3 down here. As long as these numbers here agree, so you see the 5 here and the 5 here, this is going to cancel out and give us 8. Log base 5 of 5 must be equal to 1. This is according to property 2 here, right? So as long as these agree, we get 1. And finally, 5 to the log base 5 of 12 must be 12 is an example of property 4 here. Now let's talk about the graphs of logarithmic functions and the graphs of exponential functions. So we know that the exponential function y equals a to the power x looks like this as long as the base a is bigger than 1. It turns out the logarithm is nothing more than the inverse of the exponential function. So here we have the line y equals x, and the fact that they are inverses means that if I have a point on the exponential function, there is a mirror image of that point on the logarithmic function across that line y equals x. And this happens everywhere. So for example, the point here, which is the point 0, 1, is transformed into the point 1, 0 on the logarithmic function. So if you know what the graph of an exponential function looks like, you know the graph of the logarithm is just going to be the mirror image across the line y equals x. So once we understand that a logarithm with a base greater than 1 has a basic shape like this here, we can then look at several logarithmic graphs graphed together. So here we have log base 2, log base 3, log base 5, and log base 10. And what you should see is that they all go through the point 1, 0, and they all have similar shapes, but the higher the base of the logarithm, the flatter the graph gets. One other thing to take note of here is if I have a function f of x equals a to the x, we know for exponential functions the domain is all real numbers and the range is all positive numbers. So the inverse of that exponential function is going to be log base a of x, and its domain will be positive numbers and its range will be all real numbers. And we know this because we know that domains and ranges of inverse functions are switched. So one important consequence of this that is worthwhile to remember is that since the domain of a logarithm is only positive numbers, that means you can only take a logarithm of a positive number. So whenever you have a logarithm, this number inside cannot be 0 and it cannot be negative. We can also graph logarithmic functions by plotting points. So if I ask you to graph log base 2 of x, all you got to do is find some points on the graph. Now I want you to notice that the graph of log base 2 of x is very similar to what we were looking at on the previous page. But if you wanted to graph it from scratch, what you would do is just pick some values of x. Now you'll notice that the values of x that we're picking here are not just random values of x. So since I'm plugging into log base 2 of x, I would like to plug in a number like 2 to the third power, which of course is 8. And that's because if I plug that into the function, I get log base 2 of 2 to the third, and this is equal to 3, right? Because these cancel out here. So I would pick numbers like 8, 4, 2, etc., because these are all powers of 2, known powers of 2. And when you plug those into the log function, you get the corresponding y values, and then you would sketch those to get your graph. Graphs of logarithms can be reflected using the properties that we learned previously. So for example, if I want to sketch the graph of negative log base 2 of x, we know that log base 2 of x has this graph. So putting a negative in front of it is just going to flip this graph over the x-axis. And so it yields this result. Likewise, I can graph log base 2 of negative x. Remember, when you put a negative inside of a function, that reflects the graph over the y-axis. So if this is what log base 2 of x looks like, log base 2 of negative x would be this graph here. So it's just a mirror image across the y-axis. Now, what is the domain and range and asymptote? Well, for the first one here, the domain is only positive numbers and the range is all real numbers. So if you just focus in on the red graph here, you can see that we're still plugging in positive numbers and we're still getting all real numbers. And the asymptote is right here. Logarithms have an asymptote at x equals 0. And for the other graph, you can see that when we reflect this graph over the y-axis, the domain changes. So the red graph here is defined for all negative values of x. So the domain would be all values from minus infinity to 0, and then the range is still all real numbers, and the asymptote is still x equals 0. The asymptote did not change here. Now, this might sound like it contradicts what I said a minute ago, which is that you can't plug negative numbers into the logarithm. So why am I telling you that the domain is negative numbers? Well, when you take a negative number and plug it in for x, notice that this negative will turn it into a positive, right? And so that is why the domain is changed. Graphs of logarithms can also be shifted using the same properties that we talked about before. So for example, if we have the graph of log base 5 of x, we can graph 2 plus log base 5 of x by simply shifting every point on this graph up 2 units. Now that's not going to have any effect on the domain or the range. So the domain is still going to be positive numbers. The range is still going to be all real numbers. And the asymptote is still going to be x equals 0. You can see that right here. And then the second graph, log base 10 of x minus 3, we can take the graph of log base 10 of x, and we understand that x minus 3 is going to shift this graph 1, 2, 3 units to the right. And so now we get this new graph. And this graph has a different domain, right? So now the domain is that you can only plug in values of x that are greater than 3. So it's going to be from 3 to infinity. The range is still all real numbers, but the asymptote now has been shifted. So the asymptote used to be here, but that got shifted 3 units to the right. So now that asymptote is right here. And so the asymptote now is at x equals 3. Next, we define the common logarithm. Anytime you have a logarithm with base of 10, we call this the common logarithm. And so it is a special logarithm. And the way we write it is we simply don't write the base. So anytime you see a log without a base down here, it's automatically base 10. And we do this for convenience. So for example, let's graph the function f of x equals log of x, which of course means log base 10 of x. Now to do this, what I would want to do is pick values of x that are known powers of 10. Or if they're not known powers of 10, we're going to have to use a calculator to figure them out. So for example, I know that log of 10 is 1 because log base 10 of 10 is 1. But when I plug in numbers like 4 and 5, I would have to plug those in on a calculator using the log key on that calculator. So every scientific calculator has a logarithm key, which stands for this log base 10 or this common logarithm. But you can see once you pick some values of x and plug those in, the graph of log x looks very much like the graph of all the other logarithms we've discussed in this video. And finally, we define the natural logarithm. The logarithm with base e is what we call the natural logarithm, and it is abbreviated by the letters ln. So anytime you see ln and then x, this means log base e of x. So the natural log function looks like this. So it looks just like all the other logarithmic functions, and it is the inverse of the natural exponential function. So we know that y equals e to the x looks like this. So it is no surprise that y equals the natural log of x would look like this, because once again, we have this symmetry across the line y equals x. And here we have a brief description of the definition. It's the same definition as any other logarithm. We say the natural log of x is equal to y, means that e to the y power must be equal to x. And then we have some properties of natural logarithms. These are very similar to the properties that I stated earlier. The natural log of 1 is 0. The natural log of e is always equal to 1. The natural log of e to the x is x. And e to the natural log of x is also x. And here we have some examples of those properties in use. So natural log of e to the 8, basically you can think of the natural log and the e canceling out and just giving you the number 8. The natural log of 1 over e squared. 1 over e squared can be rewritten as e to the negative 2. And now once I have that, the natural log and the e cancel out and we just get negative 2. And finally, if I give you something like the natural log of 5, we can't use any of these properties to figure that out. So for this, we need to find the button on the calculator that says LN, which stands for natural log. And then you can type that into your calculator. Now, I won't show you that here because every calculator is different. But on most calculators, you will hit this button first, and then you'll type the number 5, and then hit equals. And finally, we have finding the domain of a logarithmic function. In this case, we have f of x is the natural log of 4 minus x squared. We need to remember that whatever is inside of the logarithm must be a positive number. So 4 minus x squared must be greater than 0. Now, how do we solve this? Well, there's a couple of different ways we can solve this. One thing I would do here is I would just multiply both sides by negative 1. And what that would do on the left-hand side is it would actually give you x squared minus 4. On the right-hand side, you would still have 0, but then the sign would reverse. And the reason it reverses is because we multiplied by a negative number. Now, how do I solve this inequality? Well, I can factor. This factors into x minus 2 times x plus 2 is less than 0. And then now we're just solving a quadratic inequality. So to do this, I can just state the fact that x equals 2 and x equals negative 2 makes these factors 0, and then we can simply test each one of these endpoints. So for example, test each one of the intervals. So for example, in between here, I can use the test value x equals 0. Over here, I can use x equals, say, 5. And over here, I'll use x equals negative 6. And if you plug each one of these numbers in, for example, when you plug in 5, you will have 7 times 3, which is 21, which is not less than 0. So when you plug in 5, you get a positive number, which means this is no good, right? Because we want it to be negative. When you plug in 0, you will get a negative number. And when you plug in negative 6, you will once again get a positive number. However, as I just mentioned, we want it to be negative, because that's what less than 0 means here. So the solution is all the values in between negative 2 and positive 2. And that concludes this video lesson.